Hello guys, welcome back to the Foolish Engineer YouTube channel. This time we are going to see the working, advantage and design of synchronous type of buck converter. You might be wondering, we already have a good buck converter. Then why in the world do we need this different type? Well, you're about to find out. So let's start. This video is made possible because of Texas Instruments. If you are into electronics engineering, you probably know about this company very well. They are pioneered into semiconductors for all types of electronics ICs. Their team has provided the evaluation of synchronous buck converter, which we are going to test and understand. This is the circuit of a synchronous buck converter. It has two active switches instead of one active switch and a passive switch, unlike traditional buck converters. If you already know how this synchronous buck converter works, then you can skip to this timestamp. If not, then you can stick here. Q1 is the high side MOSFET which is connected directly to the input, and Q2 is the low side switch which we use instead of diode. During operation, when Q1 turns on, current is supplied to the load through the high side MOSFET, and Q2 is off. This time the current through the inductor increases, charging the LC filter. When Q1 turns off, Q2 turns on and current flows through this path, supplying to the load through this low side MOSFET. During this time, the current through the inductor decreases, discharging the LC filter. When Q1 is turned on, the power is supplied by the input source, and when Q2 is on, the power is supplied by the charged inductor. This step continues alternately and gives us the required output voltage. We provide PWM to these FETs Q1 and Q2, where we have to drive both of these FETs one after the another. Well, we already have this old buck converter. Then why do we need synchronous type of converter? It just adds the hassle to control one more active switch. Isn't just one single switch enough for the headache? And now we are talking about another one? Well, not really. Let's see the advantages of the synchronous buck converter over the traditional one. The synchronous buck converter has significantly lower conduction losses than a synchronous one, because MOSFETs have minimal voltage drops compared to diodes. This results in higher efficiency. Due to improved efficiency, it generates less heat, so it can handle high power without requiring extra cooling measures. Synchronous buck converters can operate at higher switching frequency because of the faster switching of the MOSFETs. And so we can use smaller passive components like inductors and capacitors. With the higher efficiency and smaller components, synchronous buck converters can achieve higher power density, so that we can use those in compact and portable devices. Next, synchronous buck converters typically give better voltage regulation compared to the older asynchronous buck converter. And MOSFETs used in these converters have better current capabilities compared to the diodes, which allows them to handle higher currents. Synchronous buck converters can often accommodate a broader input voltage range without compromising efficiency, making them more versatile for various input sources. So in summary, synchronous buck converter offers high efficiency, reduced heat generation, higher switching frequency, and better voltage regulation compared to an asynchronous buck converter. So we saw how it works, its advantages, and also how complicated it is to control this converter. So to make our life easier, we'll use power management ICs. We'll try to design a buck converter using TI's LM5160 IC and test its synchronous buck converter evaluation board to the fullest. Well, there are different ICs out there, but I selected this IC based on its advantages and features. It has a wide operating voltage from 4.4 volts to 65 volts. It has internal high side and low side MOSFETs. It has 2 ampere load capacity, wide switching frequency range all the way up to 1 MHz, and it has additional features like under voltage protection, over current protection, over voltage protection, and over temperature protection. This IC takes care of all the control mechanism hassle. We just need to connect the passive components like inductors, capacitors, and resistors according to the calculations. Well, we can break down its functionality based on the working of the converter. Pin 3 of this IC is a VIN pin. It supplies the power input to the converter and IC's internal circuits. Right after that, we have the VCC pin number 5, which is the output of an internal regulator which supplies the power to the internal circuits. And pin number 11 and 12 are called switch nodes. As you can see, these are the high side and low side switches. This pin 8 is a feedback. It handles vital task of providing regulation based on the output voltage and current requirements. Next is pin number 6, SS pin. It's soft start feature ensuring a smooth and gentle power up sequence for the circuit. It reduces the startup surge and stress. This overall feedback circuit needs to work in harmony using constant frequency. This frequency is selected by using R on pin. Next pin is pin number 10. It is the bootstrap pin. We connect a bootstrap capacitor between this pin and switch pin. Do you know why? Well, to drive the internal high side FET using bootstrap method, which we have already seen in one of our previous videos. Don't know how it works? You can check on this timestamp here. This next versatile pin combines under voltage lockout and enable functionalities. Using this pin of the IC, we can program under voltage protection for this circuit. If the voltage applied to this pin falls below the threshold value, the IC will go into under voltage mode and won't start again. Next up, we have the power ground and analog ground pins, ensuring the proper grounding for analog circuits and converter. Now let's see how we can use this IC to design a synchronous buck converter that delivers a constant 5 volts output and supplies the current of 1.5 amperes. We'll design this converter such that its input voltage would range from 10 volts to 60 volts. Remember, if you want to design a buck converter, the input voltage should be greater than the output voltage. Well, you may be wondering that I have to do all of these components calculations and selection. It will be a tedious task, but here's the best part. TI provides a handy calculator to reduce that effort. No need to grab pen and paper, just input your desired specs and the calculator does the heavy lifting. Let's see how to use it. First is the minimum, maximum and nominal input voltage which can be fed to the converter. My output voltage and current requirement is this. Then it will ask the under voltage threshold and desired hysteresis from which it will calculate the resistor values. Then we have to calculate the feedback resistor values according to the required output voltage. After that, we need to select the switching frequency using R on resistor. Then we need to select the right inductor value, soft start conditions, and finally input and output capacitor calculations. Once we have all of the calculations sorted out, we'll have a clear idea of which components we need to bring your circuit in the life. And that's where this LM5160 buck evaluation module from Texas Instruments come into picture. It is specifically designed with the same specs that we designed right now. It features the LM5160 IC itself, an inductor, a bunch of resistors, and input-output capacitors. If you look closely, you can see how small this design is. And that's the beauty of a synchronous converter. Now, it's time to see this circuit in action. We'll connect our DC power supply and now we'll fire up our oscilloscope. And don't forget here, I have connected an electronic load which will sync all of the power from this power supply and will get the optimum result. This electronic load will show us how much voltage, current and power is being dissipated through this. I can change the resistance of this load so it will sync the current accordingly. Now I will turn on the power supply. So the input voltage is around 18.8 volts. And here the output voltage I can see is around 5 volts. And now I will turn on the load which will sync all of the current. Well, you can see the load is on. So you can see the current is around 1.48 amperes. Now let's put this converter to the test and check some important parameters. First up, we'll explore the output voltage regulation in relation to the changes in the input voltage levels. For that, I have connected two probes of this oscilloscope to the input and output. And here you can see the waveforms of those. The first cursor is the input voltage and second cursor is the output voltage. Now I am turning on the load again. So as you can see, it is drawing some current from the input. Right now the voltage is around 17 volts. Now I'll go all the way up to, let's say, 10 volts. You can see still the output voltage is constant. And I change the voltage all the way up to, let's say, 30 volts. Then in that case, if you see here, still the output voltage is constant. That means the output voltage is regulated all the way from 10 volts to 30 volts. That is what we have designed for. So here you can see the output voltage will remain constant because the duty cycle adapts according to the requirement. During this time, the input current requirement of the converter also changes. Now if I decrease this voltage, so as you can see, when the voltage is around 7.2 volts, the output voltage falls to 0. That is basically the under voltage lockout. So as the input voltage goes below any certain limit that we have, let's say, designed for, then this power converter will turn off. Now when I increase the input voltage again, we can see the 5 volts output right away. Now we'll see the rise time of this converter. That means how much time does it take to turn on. So for that, right now I'm turning it off. So as you can see now, the DC to DC converter is taking around 5 milliseconds to turn on. Now I will tweak the load requirements to see whether the output voltage remains constant or not, even if I change the output current. So for that, I am changing the output resistance. So as you can see, as I am changing the resistance, the output voltage is changing a little bit. And if I go all the way down to, let's say, 400 milliamperes, then the output voltage would be around 4.98 volts. And if I again increase the load current, the output voltage will drop. But this drop will be very less. It is in tens of millivolts. So that's how we check how a particular DC to DC converter would work when we change the output load current and change the input voltage. Its output voltage should stay constant. Well, that's a wrap. This is how we can design synchronous buck converter. So what do you think? Would you like to see some more videos like this? If yes, please let me know in the comment section below. And don't forget to hit that subscribe button as well for more exciting videos. I'll see you in the next such amazing video. Till then, stay hungry, stay foolish.